Hey there, how's it going? So in this video we're going to be looking at the chain rule, and this is what we're going to use as, again, a generic kind of tool to apply to lots of derivatives once we know how to differentiate different functions. This is going to apply when we have a composite function or a function of another function. Okay, so like in the previous two videos, we will kind of give a bit of motivation to get to the rule by connecting it first with something that we can do without the rule. Then we'll try and figure out the rule that properly governs this behavior. So let's consider a function of a function like this. Alright, so here we have, right, with the brackets or the parentheses on the outside squared, right? So we have a function, our squaring function, and instead of just having like x being squared, we've got this other function, 3x plus 1 being squared. Okay, so this is of the form of a composite function, where, say, we have f of g of x, where our g of x on the inside is 3x plus 1, and what's being, g of x is being inputted into the f function, so the f function is, I'll get there, x squared. Alright. Okay, so hopefully that refreshes that it's a composite function. So as with before, what we'll do is we'll manipulate it algebraically first before we differentiate it. Okay, so since it's a perfect square, we're going to have the first term squared plus double the product, which is 1 times 3x, double is 6x, plus the last term squared. And then, since we've got like a sum of a couple of functions, powers of x with constant multiples out the front, we know how to do this, right? So we can differentiate this by going, okay, the derivative of 9x squared is 9 times the derivative of x squared, which is 2x. 9 times 2x is 18x, plus the derivative of 6x is 6 times the derivative of x, or just, it's a linear function, so it's got a constant gradient of 6, plus the derivative of 1 is 0, okay? So hopefully we're happy that the derivative of 3x plus 1 all squared is 18x plus 6. Alright, so let's say you maybe had a bit of a gut feeling of what to do with the rule, is maybe you've kind of got this big chunk of brackets here and you're squaring it. So maybe your gut feeling might have been to do something like treat like this whole thing, right, the f function on the outside x squared is like your main function, and you're going to differentiate that function, right? So if we differentiate, right, whatever this bracket function is squared, bracket squared, well, the derivative of bracket squared is going to be bring the power down and subtract 1 from the power. And then what happened to be inside the brackets? Well, 3x plus 1. And then to the power of 1 is just itself, and if we distribute the 2, we've got 6x plus 2. So that's not quite exactly the same, but at least it's similar in that, right, we've got like plus in the middle, we've got just a constant times x and then a constant number, so it's in the right kind of ballpark. And what's missing though? Like how this is kind of close, but how do we go from 6x plus 2 to 18x plus 6? Well, we're missing a factor of 3, right? If we times 6x by 3, we get 18x, and if we multiply 2 by 3, we get 6. So maybe we have to times this by 3, right? And we would get 18x plus 6. Okay, but then like where's 3 magically come from? Well, you might see that there's a 3 here, and it's not just magically the first number inside the brackets or anything like that. Well, what's the connection of 3 to this whole bit inside the brackets, right? The whole function g of x, 3x plus 1. Well, 3 is the derivative of 3x plus 1. So that's what the chain rule is going to look like. We're going to like consider like the, at least for like power functions, right? Consider like the brackets or parentheses as like our big like main function. So we're going to apply our differentiation rule to that kind of big outside function, right? So like if it's brackets to a power, bring the power down the front of the brackets, subtract 1 from the power. But then the extra thing we need to do with the chain rule is times by, if we've got a function inside there, times by the derivative of that function. Alright, so hopefully that kind of gives a bit of an idea of what to do. But again, why is that the case, right? Using the actual definition of the derivative. Alright, so we'll do that now. Let's consider y equals f of g of x. And we want to find the derivative of this. So the derivative is going to be the limit as h goes to 0 of inputting x plus h into the function. So everywhere we see x, we're going to replace it with x plus h minus the original function, so just x into the function, all over h. Okay, now, before we continue, I just want to refresh where h came from. If you remember, real quick sketch and rub it out. Remember if we had like some function, right? We were taking the limit as h goes to 0 of the difference quotient, right? The gap between these 2 points here. So this was our first point, x, and this was x plus h was the coordinate there. And so h is the gap between there, right? Because if we do x plus h minus x, we of course just get that distance is h. But I just wanted, before we proceed here, recollect that in this difference quotient with the definition of the derivative, that while we obviously just write that as x plus h minus x simplifies to h, what that h is telling us is kind of lost in the fact that we write it as a single term, is that it's actually the difference of the inputs into the function. Okay, so that phrasing is going to be important momentarily. Obviously, you'd hope I'm like foreshadowing rather than just telling some random stuff. Okay, so this move is going to seem a little bit cheeky. Let's times, well, let's say this limit is just applying to this here. Let's times both sides of our equation by whatever the derivative of g of x happens to be. Right, so times by 1 on that is going to be the same as dividing by it. Alright. Why might that be? Well, maybe, just maybe, the derivative of g of x, well, somewhere in there, the derivative of g of x, we can probably find an expression for that using the definition of the derivative, is somewhere in there we're going to turn up the difference of the input of the f function, right? So that's going to, hopefully, I'll explain it, become clear, certainly. But again, before we continue there, let's just see, is this kind of like a legal move, right? Well, hopefully we're comfortable with, I've done something to one side of the equal sign, do the exact same thing to the other side. But just like discussions about when we have h, we can't sub in h equals 0. Well, obviously we can't be dividing by 0 here either. So we can't have, right, this, whatever this thing is here, right, we can't do this move if the derivative is of g, the g function is 0. Okay, but hold up, when would the derivative of the g function be 0? Well, we get a derivative of 0 when we have a constant function. Right, so if we had g of x was some constant, like 2 or 5 or whatever, then this whole little setup would be like a bit dodgy. But if we had, right, because that constant will differentiate to 0. But if we have g of x is a constant, well then we're just inputting like a constant number into the function f, so who cares, right? In that context, which would like kind of unfurl this whole little cheeky move here, then we'd just be talking about putting a number inside the f function anyway. So, but we're talking about like actually substantially putting in a function with a variable in is what we're trying to achieve anyway. So it's kind of redundant there. So good to note that we can't have this derivative equals 0, but it doesn't end up really being an issue in my opinion. Okay, so this left-hand side we're just going to keep as it is. Okay, and now let's write out what this is. So again, the fun bit of this is writing out this half of this exact same stuff a trillion times. Okay, what is 1 on g dash x? Well, it is the limit as h goes to 0 of like kind of this same fraction, but if it's the reciprocal, it's going to be flipped, right? So it's going to be, the h is going to be on top, and then we're going to have g of x plus h minus g of x. All right, another property of limits, just like we had in the previous video, the sum, well, we went the other way because we had them all inside one limit and then separate it into two limits. But just like how we have, if we have like the sum or the difference of limits is the limit of the sum or the difference, likewise product or quotient as well. If we have a product of limits, that's the same as the limit of the product. So we can kind of put both of these fractions in, like we can times both of these fractions inside the same limit because it's the exact same limit, right? So that means that our h over h there is going to cancel out. And we're going to have inside the same limit, we're going to have this guy up here. All over g of x plus h minus g of x. Okay, so this is what I was kind of getting at before with the diagram and reminding us that h, like over here, just the h by itself, is really in hiding x plus h minus x, which is the difference of the inputs into the function. So here, g of x plus h minus g of x, well, g is what we're inputting into the f function. So on the numerator here, this is the difference of the outputs of the f function once we put the g function into it. And then on the denominator, we have the difference of the inputs into the f function. So this right-hand side here is actually, well, if it's the limit as h goes to 0 of the outputs of a function, the difference of the outputs of a function minus the difference of the, let me try again. If we have the limit as h goes to 0 of the difference of the outputs of a function over the difference of the inputs of a function, then that, by definition, is the derivative of that function, right? Like the derivative of the f function, just where instead of the input into the f function being just x, being a whole, no, the entire function, g of x. Okay, and then just like we divided by g dash x, now just we can do a bit of algebraic manipulation. Opposite of divide by this will be times it up to this side. Right, and this is what y equals f of g of x will be differentiating to. Okay, so when we have a composite function, one function being input inside another function, the derivative of that will be the derivative of like the big kind of like outside function times by the derivative of like the inside function, right? So that's very similar to what we had up here with this first example, right? So we had the derivative of the outside like big function here, the f function, right? The brackets, right? Bring the power down from the brackets, subtract one from the power, but then keep whatever's the same inside the brackets, and then times by the derivative of the brackets, the derivative of the inside function there. All right. So maybe we'll just do a fresh example that looks pretty similar like that, but just to get the verbalization of using the rule. Okay, so we could, again, 5x minus 3 all to the power of 4, we could, like we did here, expand out 5x minus 3 times itself 4 times and blah, blah, blah. Might be a bit of work, or you might know binomial expansions. Either way, we could, in principle, expand this out and then differentiate term by term with some constant multiples out the front using the power rule. Okay, but let's try using the chain rule here. So what we're going to do is the derivative of this is going to be, well, treat like this brackets, we've got 5x minus 3 is our g of x function, inside our f of x function is our brackets to the power of 4. So we're just going to firstly ignore what's inside the brackets and just apply the power rule here. So we're going to bring the power down and subtract 1 from the power, right? So that's doing f dash g of x, whatever's in the brackets, so that'll stay inside the brackets, 5x minus 3. But then we also need to times by the derivative of the brackets, g dash x, right? So the derivative of 5x minus 3 is 5, and then we can just tidy up 4 times 5 is 20. Alright, so that's going to probably be the most basic use of the chain rule, and in this case it was kind of a matter of, well, obviously I'm just showcasing how to use the rule, but like I said, we could in principle differentiate this without the chain rule, and this is maybe a matter of convenience, but the chain rule is going to become quite necessary and end up being used with lots of different type of functions, not really as a matter of convenience, but more of necessity. Alright, so just another way of doing this same problem, just with a little bit of different notation, which will be useful in some other contexts, is that let's say that y equals 5x minus 3 to the power of 4 is kind of like, well, it's y equals something to the power of 4, so let's call that u to the power of 4, and this is where we're substituting u as 5x minus 3, right? So if we substitute 5x minus 3 back into there, raise it to the power of 4, we've got that. But we're just kind of like distilling out the kind of separate functions, right? The function that's going, the g function that's kind of going inside the f function, all right? So we can differentiate each of these separately. dy differentiated with respect to u is going to be, well, since the variable's u, differentiating with respect to u, bring the power down, subtract 1 from the power. And then over here, we've got du, u is a function of x, and so du dx is going to be the derivative of 5x minus 3, which is 5. But if we're trying to differentiate this original function y, which is a function of variable x, we're trying to find the derivative of y with respect to x, which is kind of like, well, we've got dy over dx there. And if we put, say, a du there and a du there, you can kind of think of this like the the du on the, like, because we got multiplication across a fraction here, the du over the du would cancel out and leave us with dy over dx there. Well, if we want to find dy dx, which equals this, well, we have expressions for both of these, right? So dy dx is going to be dy du, which is this one here, 4u cubed times du dx, which is this one here, 5. And then to tidy it up, we can do 4 times 5 is 20. And u, well, u was substituted from 5x minus 3, so we can put 5x minus 3 back in, and that was all cubed, all right? So you can see we get the same thing, but just kind of different working out and arrangement. But again, trust me, this will be useful for some specific type of problems later on. All right, let's just do another example. Where we can use this. So if this was just that plus 3 wasn't there, 4 over 2x, hopefully we'd be comfortable doing that. But just like we normally do with a fraction, or like with a surd, where we'd manipulate it first to a power, or to a power, that's the one, to negative rather, negative or fractional power. Respectively, we'll still do the same approach here, right? So we're going to have 4 outside of 2x plus 3, all to the power of negative 1, right? So 2x plus 3, say to the positive 1, bring it up into the numerator, change the sign of the power, and now we've got a constant multiple times a function of a function, which we can use the power rule for. The power rule for part of it, but the chain rule that we've just learned. Okay, so we're going to have constant multiple 4 times derivative using the chain rule of the brackets, which is going to be this function to the negative 1. So bring the power down to negative 1, and then subtract 1 from the power. And then what happened to be inside the brackets? 2x plus 3. But then chain rule says we've got to times that by the derivative of the brackets, and the derivative of 2x plus 3 is 2. All right, and in the interest of space, it's not that nice neat working out. We'll just go across. So we've got 4 times negative 1 is negative 4 times 2 is negative 8. And then we can pull this with the negative 2 back into the denominator with a positive power. 2x plus 3 with a positive 2 there. All right, and one last example. All right, so like we just did, and like I just said that we've done in previous contexts, we want to use the power rule, but if we want to use the power rule, we need to represent it with a power. So we've got here that this in here is what is being square rooted, so that's what's being raised to the power of a half. So we've got x cubed plus 2x to the power of positive half. So now that we've got like a function of a function represented with a power, we can use the chain rule and using the power rule as necessary. So we can find the derivative here is going to be of this whole chunk of brackets, bring the power half down the front, subtract 1 from the power, and what's in the brackets? X cubed plus 2x. And then now using the chain rule, we have to multiply it by the derivative of what's inside those brackets there, that g of x function being inputted into the square root f of x function. So just be careful here. So far we've just had numbers, 5 and 4, but it might not be a constant, right? We could have had, instead of 5, had 5x squared, well, the derivative would be times by would be 10x. So it might not just be a number, it might be have a variable there as well. But as well as having a variable, this is also the derivative of x cubed plus 2x is going to have multiple terms, so make sure you don't write out times derivative of x cubed is 3x squared, derivative of 2x is plus 2, right? Because that whole thing there should be in brackets. Alright, so now just tidying this up, just like normally happens with square root, negative is going to come down to the bottom here. So we're going to have 2 down the bottom times negative half is going to be this with a positive half, so just basically back to what it originally was. Positive half, which is square root. And then we're going to have this being multiplied by the 1 up on the top there. And that's it for the chain rule for now. So cheers, catch you later.